Hello, my name is Morgan Fine-Morris. Today I'm going to talk about learning action models with symbolic and numeric preconditions for a Waypoint navigation system. So the learning system accepts both positive and negative examples, as well as theta, which I'll talk about later, and background information, which it uses for the numeric component of learning. There are two main components of the learning system of the learner. The first uses maxsat and the theta value to determine the precondition fluence using the positive examples, and then also it uses those to extract the effect fluence from the positive examples as well. The second component learns the numeric preconditions from the positive and negative examples and background information by fitting a logistic regression model to some of the numeric fluence, to the numeric fluence in the positive and negative examples. Then we synthesize all of that data, those three components together to make the operators. So some related work. PlanMiner and ERA both learn actions with numeric preconditions, as this work does, but the former learns very simple, like arithmetic preconditions and effects, and the latter learns a piecewise function that maps a categorical variable to one of a set of simple linear functions. Basically, it determines what the coefficient of the function will be. ARMS also uses maxsat to learn symbolic preconditions for partially observable states, but doesn't deal with numeric preconditions. And Trail and Expo both learn operators, but Trail doesn't handle noise, and Expo doesn't handle numeric values. So we generate training data using a simulator, which creates initial states that are comprised of maps, such as this one, plus the vehicle information. The simulator can also create schedules, which are a set of actions that the vehicles should accomplish, and it can simulate those schedules on the initial state to create a plan trace. The simulator has two actions, or two operators, a transit operator and a refuel operator. You can see this is an example of the state of the system after the transit action at the top. Each fluent is a state variable where the final argument is the value of the state variable. We create training examples using the simulator, first by generating a set of states and schedules and simulating them to form traces. And we can extract state action state triples from those traces for positive examples. Negative examples are made with the same states and schedules, but we remove refuel actions from the schedules before we simulate, and then extract to create a set of traces which have some non-finishing actions, and then we extract those non-finishing actions to serve as our negative examples. When we learn the precondition fluence, we take the positive examples and assume that some of the fluents in S are potential preconditions, and the fluents in S prime are potential effects, and we filter based on the number of positive examples in which fluents appear, and on relatedness, which means do the fluents share arguments with the action. Once we've filtered the fluents, we create a weighted CNF, which enforces that some of the fluents in S are preconditions and some fluents in S prime are effects, and also that in order for some of the fluents in S prime to be effects, they have to, a state variable in S prime can only be in the effects if its value changed from S to S prime. And if a state variable is in the effects, it has to also be in the preconditions. So by solving that equation with maxstat, we output these precondition fluents, which we then use to decide which of the numeric values, numeric state variable values are used to fit the logistic model, which outputs a function, outputs the numeric precondition function. The logistic model has two, we fit it to two classes. The positive examples are the true class, and the negative examples correspond to the false class. We evaluate our learned preconditions in two different ways. The first way, we compare the learned preconditions to a set of ground truth preconditions, which were hand selected. And for both operators, we try to learn the operators using different numbers of training examples, 3 training examples, 10 training examples, and 30 training examples. You can see the green and orange are 3, the blue and purple are 10, and the pale green and yellow are 30. We also add some noise examples, which are positive examples that don't, which are examples that are marked positive but actually lack one of the important preconditions. And we try to learn both without any noise examples and with some number of noise examples. And you can see that the noise examples don't significantly increase the number of false positive preconditions that are identified. False positive preconditions are preconditions which are identified as preconditions but aren't actually in the true preconditions. And you can see that as we increase the number of training examples, we reduce the number of false positives, and as we increase theta, we also reduce the number of false positives. Our second evaluation technique uses one of the sets of learned operators and a set of handwritten methods, and attempts to plan to generate plans for a set of test problems using a planner. So the planner is a hierarchical task network planner, hence the need for handwritten methods. The plans it outputs, we convert to schedules, which we simulate to verify their correctness. When we do this, we find that for thetas of 0.2 and 0.3, or which corresponds to support of 20 and 30%, the planner is able to generate plans for all of the test problems using those handwritten methods and the learned operators, but is only able to generate plans for about half of the test problems when we use the 10% support operators. All of the plans that we generated were able to be run on the simulator. So finally, here's an example TransitAction operator. You can see that I've circled the numeric component, and you can see that it uses a distance function, separate distance function, which is provided via the background information that I mentioned earlier, and it's also a function of GTLV1, which is the initial gas tank level. Yeah, that is all I have for today. Thank you for your time and attention.